Are we rolling? Are we live? Well, whether or not I'm actually live, I think is up for debate. Howdy. Okay. So here I am. Lovely Saturday. Windy as all get out. We're in a weather advisory because of the high winds. Kind of an interesting thing. Poor Jeep's getting thrashed around. Interesting topic today. This is chapter 10, as I recall. This is 10-12, actually. We have 2 more chapters after this. And we are done with what we wanted to accomplish if you're doing your part. Okay. Today we're going to talk about imaginary numbers. We have a variety of different kinds of numbers. We've talked about in the past rational numbers. Rational number is any number that can be expressed as a fraction. 1/327. That's a real number. It can be expressed as a fraction. If we convert it to a decimal, it probably, I assume, looks pretty ugly. Zero 0.003058, 104, and it continues. It's a rational number. An irrational number is a number that continues but is not expressible as a fraction. It means these decimals, and this looks irrational. This number here looks irrational because usually the way we characterize an irrational number, the decimal point goes on forever and it never repeats. 1/3 repeats, 0.3333333. Yes, it goes on forever, but it's always 3333. Square root of 2, 1.414, 2135, 62. And it goes on. The only reason those are the only digits I can give you is because that's as many digits as my calculator can give me. Both of them look irrational. If you look at the decimal, both of them look irrational. They both look like they go on forever. Neither one of them looks like they repeat. So they can trick you. But the difference is this one we know is rational because we started off with it as a fraction. I chose this number out of my disgusting beady little head. But the square root of -8. 8 can be rewritten as -4 times 2. Now, we learned some of the rules of powers. We can rewrite a square root as a power to the 1/2. And we know that if we multiply terms to the 1/2 power and So in other words, we know that we can rewrite this as this. Why would I do this? Well, we know the square root of 4 is 2. We know the square root of 2 is irrational. So the square root of -8 can be rewritten as the multiplication of several terms, including a rational term, 2 is a rational number, and an irrational term. Square root of 2 is irrational. The number as a whole, square root of 8, is irrational because there is no answer. Well, the answer is much like this. It goes on and repeats forever. But it can still be thought of in terms of a rational part. A rational part an irrational part, and a part that we have not discussed yet. This is imaginary. The square root of -1 is imaginary. Why? Well, remember what the definition of square root means. When we take the square root of a number, like the square root of 4, we're looking for a number where when multiplied by itself, we get the number back. If we take 2 and multiply it by itself, 2 times 2, we get that 4 back. That's what the square root is. What times itself will give us back a -1? We know the square root of 1, that's just 1. But +1 times +1 gives us a +1. -1 times -1 gives us +1. +1 times -1 is not a number times itself. +1 and -1 are two different numbers, so it does not fall. Positive and -1 does not fall in the definition of the square root. What this is telling us is that there is no number that times itself will give us back a negative number. That's why this is imaginary. It really cannot exist. It's a wonderful little whimsical term for a number that just cannot exist. The book assigns a letter to this. Lowercase, well, now we have to be careful. The book assigns this the lowercase j. I've seen that before. I forget where I've seen it, but I know that I've seen a book where it was defined as lowercase j. But when I first learned this, and most of the time, most commonly, every once in a while you will see it as j, but most commonly you will see it as lowercase I. So if you don't mind, for our discussion today, you're going to call it I rather than j. Just understand that in the book, I is the same thing as j, and it is a definition. Whether you use I or j, it's a definition. It is the square root of -1, and it's a definition because we know that it cannot exist. Okay? I need to remember this board has that funny pen there. I think what happens is engineers, for some reason, prefer to use J rather than I, but I don't know why. So, lowercase I is the same as lowercase j is defined as the square root of -1. Today we want to look at some properties and uses of this. But before we do, I want to talk about an application. The biggest application that I'm aware of for imaginary numbers is quantum theory. It's quantum mechanics. When we talk about wave properties of electrons, well, see, I'm a chemist, so rather than quantum mechanics, I tend to talk quantum chemistry, which is quantum mechanics as it applies to chemistry. And most of the time when we talk about quantum chemistry, we're talking about the behavior of electrons. Electrons surround the nucleus of an atom. They are on the outside of an atom, which means when atoms interact with each other, which, let's face it, whenever there's a chemical reaction, whenever there's a chemical process, we're talking about atoms interacting with each other. And it's really those electrons that interact with each other because they're on the outside. So when we talk about quantum chemistry and the behavior of electrons, we're talking about chemical behavior. Now, in quantum theory, imaginary numbers are used frequently, which may feel like it's a problem. But these imaginary numbers are always squared, which means the imaginary part always disappears. We'll talk about that in a bit. But I want you to understand that even though we're calling this imaginary, understand that there are real-world applications to it. When we talk about quantum mechanics, we are talking real-world application. Hey, I got something today. Do you want to see it? No, not today. I got Friday. Do you want to see what we got? I'm so proud of this. This there you go. This is our accreditation. This is what now? See, this is the ASCLD. No, this is the ASCLD Lab Accreditation Certificate, which means our forensic lab is now accredited. I'm so proud of that. Has nothing to do with what we're talking about, but it's sitting here, and I just had to share. Being accredited puts us on the same footing as any other forensic lab, not in the nation, but in the entire world. When you're talking about the FBI lab, when you were talking about the Interpol lab, when you're talking about Scotland Yard forensic lab, doesn't matter what you're talking about. All of them have to be accredited to the same standards that we are now accredited. Kind of a cool thing. All right, let's talk about imaginary numbers. First thing your book talks about, and I gave you an example. Anytime you're taking the square root of a negative number, you're going to write it like this, where I is the square root of -1. So you take the square root of the number as if it's just a number. But then you have to remember, because you have a negative in the square root, you have to remember to put that I in there. The first application that the book uses is the quadratic equation. When we first encountered this, long time ago, I threw up an example where I just made up values for A, B, and C, and I threw them in there. And we actually could not calculate the values of x at that time. Because we ended up with a value where 4ac was greater than the value of b squared. In other words, we got a negative number in the square root. At the time we hadn't talked about imaginary numbers, so I really could not, in good consciousness, throw out an I without going into a rather prolonged discussion of what I is. How prolonged? Well, the exact length of this particular video. But if we could reverse this so that the 4ac was positive and the b was negative, so we're talking about a case where b squared minus 4ac, what is inside this square root, is less than 0. In other words, it is negative. Then we can rewrite this. This is what the book does. Like this. In other words, we flip the two by taking the negative of the flip. Now, you can work this out. This makes sense. Remember, the negative times parentheses means you multiply this by every term inside the parentheses. So negative 4ac gives us this negative 4ac. Negative of a negative b gives us a positive b. Oop, squared. Sorry. Gives us a positive b squared, which this is a positive b squared. So this is completely accurate. It is exactly the same thing. In the end, we recognize that this number will be positive. But we still have this negative 1 right here. Well, this we now know how to deal with. Because just like we saw the example of the square root of negative 4, it was just 4 times I. By the way, most of the time you'll see the I or the J if you prefer after the number. But if you still have a square root term, you put the I where it's most visible. So sometimes you'll see it in front just so that it's more visible. Well, since we know in the end we're going to end up with an I value anyway, we can go ahead and pull that out now. Now we're not going to put the I on the end. We're going to make sure it's very clear it's on the outside. So we're going to go ahead and put it here. And we get this. And this is what the book has, only instead of I, we use a J. Almost said a B. It's not a B, it's a J. Don't confuse B with J, because B and J are not the same thing as J or I. BJ has a very specific meaning that kind of beyond the scope of this particular course. Okay. Do we have to remember this formula? Hell no. Here's the example that the book says, that the book gives. Suppose we have x squared plus x plus 1 equals 0. Well, in this case, note that a is equal to 1, b is equal to 1, and c is equal to 1. Well, that's a really simple example. So what is the solution? B is equal to 1, so we have negative 1 plus or minus the square root of b squared, which is 1 squared, minus 4 times a, which is 1, times c, which is 1, all over 2 times a, which is 1. 1 squared is 1. 4 times 1 is 4. 2 times 1 is 2. Therefore, I think I showed you this symbol before. The book uses a new symbol here as well. It uses sort of an open arrow kind of a symbol where it looks like an equal sign with a little. I use 3 dots, 1 above and 2 below, almost like delta. 3 dots means therefore. It's not quite the same as that arrow, but it's similar. We get -1 plus or minus the square root of -3 all over 2. Well, now we know how to deal with the negative. If we have a negative inside a square root, we're going to get rid of the negative and replace it with an I or a J. I don't care which one you choose to use. Either one is fine. The book writes this as 2 different fractions, which is fine as well. -1/2 plus or minus I times the square root of 3 over 2. I just wrote that as a J. This is kind of an interesting way to rewrite it, and it's fine. You know, they split it up, and that's okay. If we wanted to, we could actually get rid of this -1/2 and just flip the plus minus. You'd find it's exactly the same, but that's fine. We'll keep it as it is. What's interesting about this is I've talked about 3 different types of numbers: rational, irrational, and imaginary, and this gives us all. The rational part is the -1/2. 1/2 is a fraction. That's a rational number. We have an irrational number because the square root of 3 is irrational. So we have an irrational part to the solution. And the irrational part, the irrational part is also the imaginary part. Okay? Now, this really is just a couple of examples of how and when it might come up, and how to deal with it, how to handle it. But we do have to know a little bit about how these, how irrational numbers behave. My computer just went to sleep. I think it's trying to tell me something about how exciting the lecture is, so I'm taking it personally. Okay. So let's talk about how these irrational terms I, or if you prefer J, behave. How do you handle them in regular algebraic equations? And the answer is very simple. You treat them as if they're a variable. They follow all of the same rules that variables follow. Until you get to the very end. Then there's a couple of things that you need to know. But for example, let's look at this expression. 4i times the quantity 3 plus 2i minus 6i. How do you simplify this? This is not an equation, but we want to simplify this expression. Well, like I said, For the time being, we can ignore the fact that we know the value of I. We can pretend like it's just a variable because it follows all of the same rules of any variable. In other words, when you multiply, you carry it through. We're going to have to multiply by 3. We're going to have to multiply I. I'm really worried, you know. Just kidding. I was going to make a joke about the Ashley Madison scandal. Ooh, they might find my name. If you want to know the truth, I'm more worried about seeing my ex-wife's name in that list than mine. I know my name's not in the list, and if it is, someone stole my identity. It wouldn't surprise me if my ex was in there. Anyway, we're going to keep multiplying the I by every term inside the parentheses. This 6I is not inside the parentheses. Therefore, we are not multiplying the 4I by the 6I. The 6I we're going to leave alone until we get to addition and subtraction. So, first thing we're going to do is multiply out. 4I times 3. There's no I value here, so we just carry it over. 4I times 2I, I times I. Just like we multiplied the 4 and the 2, we're going to multiply the i's, and we get I squared. And we bring down the 6I. Now, when we add or subtract, we cannot subtract 6I from 8I squared. They are both i's, but remember, when dealing with a variable, you can only add or subtract if two conditions hold. The variable is the same, in this case they are, and the powers are the same, and in this case they are not. Because these powers are different, we cannot subtract these two terms. But, and this is a big hairy but, these two have the same terms, they both have i's, and they're both to the first power. So these two terms we can subtract. 12 minus 6 becomes 6. The variable is not really a variable, but we have 6I plus 8I squared. Are we done? Not quite. Because we also have to worry about how I powers work. That seemed a little odd. How do I powers work? Well, let's do this off to the side here. Let's rewrite this. I, or j if you prefer, is the square root of -1, which is the same as saying it is -1 to the power 1/2. Remember, 1/2, that's the square root. I've not had any Diet Coke today, so I'm going through this rather quickly. What's I squared? Remember, when you have the same number raised to powers, you add the powers together. 1/2 plus 1/2 equals 1. In other words, I squared is equal to -1. 8 times I squared is the same as 8 times -1. This is positive. A positive times a negative tells us that our final solution here is actually 6I minus 8. Because I squared means we're multiplying by -1, so the positive becomes a negative. Okay? Let's continue. I cubed. I cubed is the same as I squared times I. We know that the value of I squared is -1. or negative I. I cubed is negative I. That's all it is. I cubed, nothing more than negative I. About I to the fourth power. Well, I to the fourth is I squared times I squared, which is negative 1 times negative 1. I to the fourth power is positive 1. We can go on forever at this point, because every power of I beyond 4 is some combination of 1, 2, 3, and 4. I to the fifth is I to the fourth times I. I to the fourth power is 1. I to the fifth is the same as I. I to the sixth power is I to the fourth power times I squared. I to the fourth is 1. I squared is negative 1. And we get negative 1. And you're starting to see a repeating pattern. I to the seventh power is negative I. I to the eighth power is 1. I to the ninth power is I. I to the 10th power is negative 1. I to the 11th power is negative I. I to the 12th power is 1. And it just goes on. The 4 that you should remember, and I hate giving you memorization, but keep in mind, you can always figure it out. And I don't know why, but for some reason these 4 really clicked in for me. Here it is. Well, we start with I, which is the square root of negative 1. I squared is negative 1. I cubed is negative I. I to the fourth power is 1. Beyond that, take out however many I to the fourths you have, and then just kind of see what you're left with. All right. That's it. Well, at least for this part of the chapter. The next part, they start talking about plotting it, and they do this in quantum mechanics every once in a while as well. I'm not going to worry too much about it, except for one thing. They introduce a new concept here without really going into it. And I want to introduce that graphing concept to you. Here's what they do. They make a plot. And in their plot, and like I say, you see this every once in a while, especially in physics journals. Because sometimes, because quantum mechanics has that imaginary part, our solutions, we can't have imaginary parts. So there are certain mathematical tricks that physicists have to do to get around the fact that part of their solution might be imaginary. And what they really do, they define the x-axis as the real axis. The y-axis is the imaginary axis. So if you want to plot a point that has both a real and an imaginary component, the real is going to be the 3, the imaginary is going to be the 2, and your point is right here. That is really no different than just any other Cartesian, except remember that along the y-axis we have the imaginary component. I'm going to draw this a little bit larger. I realized I drew that kind of small. drew a point here. This point was drawn in a Cartesian coordinate. The x, or the real component, was 3, the y, or the imaginary component, was 2, and guess what? We have a point. But there is another way to draw this point. These are called polar coordinates, polar spherical coordinates. Polar spherical coordinates, and there are other coordinate systems as well. Do not think that these are the only two coordinate systems there are. There are others. There's cylindrical coordinates. I did a rather complicated project on DNA. And for DNA, cylindrical coordinates actually are far better than Cartesian or polar spherical. So this is just an introduction to a much, much, much larger world. Here's how you do polar spherical coordinates. To draw this point, what we really need are two things. We need the distance from the origin to the point. We call that the R value. Unless you're a chemist telling a joke instead of R, then it becomes the RR value. RR. Sorry. I apologize. But I will say this, is because of this distance that this is actually the favorite coordinate system of pirates. Arr! All right. So we have our arr. How far are we? How far are we from the middle, from this 0, 0 point? It's not enough. It is not enough. The second number that we need is this angle, which we call theta. If we're plotting in three dimensions, then we need another angle to sort of talk about how far around this way we are. But in 2 dimensions, all we need is the angle of the inclination and the distance from the origin. And guess what? Any number, any point, like any point that can be plotted using Cartesian coordinates can be plotted using these 2 values. Now, do you recall the most famous reindeer of all? This length, which is the y value, this is opposite of our angle. This distance, which is our x value, this is adjacent to our angle. Recall the most famous reindeer. I've got to stop using that joke. It's just a dumb joke. But that's all right, because I tell dumb jokes. Recall trigonometry. Sine is opposite over hypotenuse, which is x over r. Cosine, oh, I have this backwards. I have it backwards. Opposite is our y value. My bad. Adjacent is our x value. So we have a relationship. And by the way, remember Pythagorean's theorem, r, or r squared equals a squared plus b squared, r is simply the square root of x squared plus y squared. Okay, these are not the formulas you need. They're not the formulas that you need. But if you're trying to convert or relate, if you're trying to relate spherical to polar, or spherical to Cartesian, or Cartesian to spherical, this is just showing you that there are relationships that give them to you. So, if you have your that work. If you're given polar coordinates, and you want to go to Cartesian, what we need is x and y. And these are really simple. Your x value is r times cosine theta. Your y value, and all I'm doing is just algebra here, your y value, just multiply both sides by r, is r sine theta. Very simple, given r and theta, to get x and y. Very simple thing. A little more complicated to go from Cartesian to polar spherical. Well, r is here. To get r, r is x squared plus y squared. Boy, I tell you, in chemical simulations, we use this all the time. It is so common to want to think in terms of x and y. It's what we're all used to. It's what we all grew up with. By the way, here's this. But two atoms, if you're trying to calculate the interaction between two atoms, they really don't care what their orientation is in the x and y axis. It can be anything. What they only care about is their absolute distance from each other. That's all they care about. And that is what this r is. The absolute distance between these two. Now you throw a third particle in here and all of a sudden you need to start worrying about the second dimension. Throw a fourth particle in and you need to start worrying about the fourth dimension. By the way, why? Why 3 do you only need a plane? Well, remember, how many points define a line? 2. 2 points define a line. 3 points, as it turns out, is all that is required to define a plane. 3 points will define a plane if, and only if, those 3 points are not all in the same line. If they're all in the same line, they're all part of a two-dimensional system. If you have 3 points that are not in a straight line, 3 points define a plane. You do not need to get into the third dimension until you get 4 points. With a 4-point system or greater, you finally have to get into the z-axis, which comes out this way. Now, what about theta? Well, remember, theta, there's a couple of different ways you can do it. You can do it using sine or cosine, but the most obvious, remember tangent? is opposite over adjacent. So the tangent of this is your y divided by x. The opposite over the adjacent. Therefore, theta is the anti-tangent. The inverse tangent, I'm sorry, not anti, is the inverse tangent of y over x. Did I do that right? Yes. Okay? By the way, notice two things. Very easy to get into this part of the coordinate system. Remember, this is part 1. This is our first, what do you call it? This is 2. This is 3. This is 4. Kind of a complicated board today, isn't it? To get into the second region, all it means is the angle theta has to be greater than 90 degrees. So if you have an angle theta that is greater than 90 but less than 180, then you're into region 2. Region is not the right word. Do you remember what the right word is? Because I don't. At the moment, I kind of forget. To get down into region 3, there's 2 ways to do it. We can just continue on with theta. Theta equals 180 would be sitting here. So if theta, if this angle is greater than 180, but less than 270, we're here. So that's one way to do it. But notice, we can keep theta less than 90 degrees and just use a negative value for r. And both of them will put us down here. By the way, typically, you want theta to be, you want to keep r positive. But remember, the square root always has 2 roots, positive, negative, so that would work as well. To get into region 4, theta has to be between 270 and 360, which means that the angle has gone around nearly 3/4 of the way, beyond 3/4 of the way. Or you can have a theta between 90 and 180 with a negative value for r, and that puts you in region 4. So all 4 regions, 1, 2, 3, and 4, they are all there. They're all right there. All right. Finally, the book gives you one more quick definition. But again, they throw it up. They just barf it up and don't give you any explanation as to why it's important or what it means. So I'm going to barf it up as well, show you what it is, and I'm not going to use it, but I am going to tell you at least where it applies. I've heard this pronounced many different ways. I believe the correct pronunciation is Eulers function. But I might be wrong. Like I said, I've heard it many, many, many times, but always different every time I do. This is Eulers Formula. The book just kind of says, oh, there it is, oh, Eulers Formula. What a worker! All right. So what? All right. There's a couple kind of cool things about Eulers' formula. First of all, notice that it has both a real and an imaginary component. And it takes both a real and imaginary component and it combines it. And this, by the way, is mathematical. This goes back to those what were they called? The H trigonometry functions. The hypergeometric functions. This goes back to those hypergeometric functions. So we have basically a single term, and I know something about singles. Oh, they're all fucking crazy. We have a single term that actually expands out into both a real and an imaginary form. I'm used to seeing this with a slightly different form. If you have negative up here, you get a negative here. Like this. So what? This is the waveform for quantum mechanics wave functions. When we talk about behavior of electrons, we talk about wave functions, which helps us to understand their behavior. The wave function does not talk about how the electrons move. In quantum mechanics, we're not allowed to know how the electrons move. That is actually the foundation of Heisenberg's uncertainty principle. We can never know, and by the way, this is a mathematical proof. When we're talking about something the size of an electron, we cannot know its exact position, that is to say where it is, and momentum, that is to say the direction or the velocity at which it is moving. We cannot know its position and momentum at the same time. So, we were forced to come up with a brand new form of physics. The old form of physics, we could always calculate exactly the location and the movement of particles. I remember doing this beautiful example. When I was in high school, we took a ruler and we made an incline out of it. Probably have to tell it to you this way. On a table. And on this incline, we would start the marble down, and we had to calculate its velocity. Then, based on its velocity, we knew how tall the table was. We had to calculate, based on how fast it's going to fall once it comes off the edge of the table, we had to calculate exactly where it was going to hit the ground. And they gave us a little Dixie cup. Remember those little paper Dixie cups that could hold almost 3 drops of water? We had to put that on the ground. And that's how we were graded. Without trying it, we had to call the teacher over the first time and say, okay, we're ready. Here's our Dixie cup. And we ran it, and if it went in the Dixie cup, we passed. Well, guess what? That's classical mechanics. That is Newtonian physics. You're allowed to know exactly where everything is. You're allowed to know exactly where its velocity is and what direction it's going. With something the size of electrons, we can't. We had to throw all that out. That was one of the biggest problems with predicting chemical behavior. It was just we had to get away from that paradigm, from that concept of knowing everything. And Heisenberg is the one who said, you can't. Screw it. Fortunately, a lot of people who are a lot smarter than I am said, fine. If we're not allowed to know exactly where the electrons are and exactly where they're going and how they're moving, where are we most likely to find them? And quantum physics is not based on Newtonian physics, it's based on probability. Where are you most likely going to find that electron? And that's what the wave function gives us. The wave function gives us the probability of finding the electrons. If we stand in one location, if we want to meet, well, let's say we want to meet Mel Gibson. We have not had our quota of crazy today. We want to meet Mel Gibson. Where are we going to stand? Are we going to stand here in Rapid City, or are we going to stand in Hollywood? Where are we most likely to cross Mel Gibson's path? That's the way that we think in quantum mechanics. Where are we most likely? And by figuring out where we are most likely to find the electron, that relates to where the electron is spending most of its time. And if we can figure out where it spends its time 95% of the time, that allows us to calculate charges around a particular molecule, because 95% of the time it's here, so that's where most of the charge is going to be. And from the charge, we can calculate all kinds of nifty things. The wave function looks something like Eulers formula. It has an imaginary and a real component. The only thing really missing here is the R value, which we usually put in front, which is the same thing as taking these values and multiplying them by R. So we have distance, and we get the angle in both the imaginary and the real plane, and that's where Eulers' formula comes into play. I'm sure there are other applications as well. Are we going to do that today? Oh, hell no. You're not ready for that. But you're getting there. It's interesting, don't you think, that it's interesting that you are doing a self-imposed pre-algebra course, and we are already talking about advanced quantum physics. It's the foundation. It really is. That's what you're working on right now. I think it's a cool thing. I hope you think it's a cool thing. I hope you're not wasting my time, and I hope you're still watching these bloody things. But you know what? Whether you are or whether you're not, I'm doing it for you because you asked me to. And I'm happy to do it for you, and I'm kind of enjoying it, and I hope that you are as well. So I will see you next week. We have 2 more. Means we are 80% done with these things. If you're watching this and wondering what happened to Chapter 9, recall we elected to skip Chapter 9 because in the book, Chapter 9 is really just practice examples from Chapter 8. So anything you need in Chapter 9 we've already covered. And Eulers, see you another day.